Hello students, welcome to EPG Pathshala and myself Reema Gupta from University of Delhi. Today we are going to discuss about the module Alumina and Zirconia Ceramics, and this is from the paper Ceramics. So after completing this module, you shall be able to understand the concepts and the basics of alumina ceramics and zirconia ceramics. So before moving further, let us discuss some bases about it. So the polycrystalline alumina. So the polycrystalline alumina has very good mechanical properties which make it useful as a structural ceramics because of its properties of transformation, roughening, and zirconia ceramics can be designed to have very high fracture roughness, which is the advantage of such type of ceramics. So the zirconia particles can also be used to toughen other matrix such as alumina, and these two structural ceramics are discussed in this module one by one. So the first structure which we will be discussing is alumina. Alumina is also known as alpha alumina. So the alpha alumina has a rhombohedral structure with space group R3C. The lattice parameters at room temperature when referred to hexagonal axis are A is equal to 0.4759 nanometers and C is equal to 1.299 nanometers with a coordination number Z is equal to 6. The structure is best described as an AB-AB hexagonal close pack stacking of the O2 minus ions with Al3 plus ions located at 2/3 of the octahedral interstitial sites. So students, you can see this structure on the left hand side of this slide. Alumina has mixed ionic and covalent bonding with a very high enthalpy of formation, that is 1600 kilojoules per mole. This makes alumina one of the most strongly bonded compounds. So alumina is one of the most strongly bonded compounds with a very high melting point of 2050 degrees Celsius and a very high hardness of 9 on the Mohs scale, on which the hardest material known, that is diamond, has the hardness of 10. The strong atomic bonding of hexagonal structure make the dislocation motion very difficult in alumina. Some basal slip on the basal slip system, that is 001-1120 plane, occurs above 900 degrees Celsius. However, most of the alumina ceramics have siliceous phase at the grain boundaries, which flows and causes deformation above the temperatures varying from 800 degrees Celsius to more than 1100 degrees Celsius, depending on the purity of alumina. So students, let us discuss about the properties of alpha alumina. The properties of alpha alumina ceramics depends on the purity and the microstructure. These ceramics can have high elastic moduli, high hardness, good tribological properties and wear resistance. It also has good mechanical strength and high temperature stability. However, not all the properties are at their best levels in a single material. So the processing and the microstructure have to be designed to optimize the properties relevant to a particular application. The properties of alumina ceramics can vary over a wide range, which we will be seeing in the next slide. So this table illustrates the properties of alpha alumina. So students, you can see different properties of alpha alumina like density, Young's modulus, stress intensity factor, fracture strength, Weibull modulus and hardness. So students, you can see that the hardness of alpha alumina is 2100, whereas the density is 3.98 gram per centimeter cube, whereas the Young modulus is 400 gigapascal at room temperature, whereas the stress intensity factor is 3.44 with the units meganewton per minus 3/2. However, the fracture strength, that is in bending, is found to be 400 megapascal, whereas the coefficient of thermal expansion, that is alpha, varies from 5.5 to 10 into 10 to power minus 6 per Kelvin. Moreover, the melting point of alpha alumina is 2050 degrees Celsius. Manufacture of alpha alumina. The bauxite is the ore used to manufacture alumina. It consists mostly of the minerals gibbsites, that is aluminium hydroxide AlOH whole thrice, boehmite gamma AlOOH and diaspore, that is alpha AlOOH, mixed with some clay, that is kaolinite, and small amounts of oxides of iron and titanium. Most of the bauxite is used to produce the metal aluminium by the Bayer's process. So Bayer's process is a very famous process, and intermediate products in this process is hydroxide of aluminium called gibbsite, that is AlOH whole thrice. The calcination of gibbsite results in its dehydration, followed by crystallization to many types of transition alumina, which is followed by alpha alumina. On cooling, the alpha phase remains stable. However, in addition to gibbsite, many other hydrous phases of alumina are also known. A natural mineral is diaspore, and this diaspore has a chemical formula Al2O3.H2O, that is boehmite, and alpha AlOOH is a component of the bauxite ore. Barite is a structural polymorph of gibbsite. All these forms are also the components of bauxite ore. These phases undergo phase changes at different temperatures and ultimately form alpha alumina, that is the most stable alumina. Moreover, the purity of the powder must also be high, that is, it should be greater than 99.7%. The alpha alumina powder needed for the preparation of ceramics is obtained by heat treatment of the transition aluminas at temperatures of about 1100 to 1250 degrees Celsius and then milling. So the product is called calcined aluminas. The calcination temperature has to be controlled to yield the powder of fine size and high reactivity, which sinter at lower temperatures to high density. The powders sold by different manufacturers differ in their reactivity, which is a function of proprietary powder preparation treatments and the highly reactive and fine powder supplied by some manufacturers can sinter at temperatures as low as 1500 degrees Celsius to a high density, while the other may require temperatures of 1650 degrees Celsius, and for the most demanding application such as intrinsic ceramic, optics and electronics, the purity of the powder must also be high. Now students, let us discuss about the application of alpha-alumina. As a structural material, the tribological applications of alumina are most important. It is used in thread guides in textile industry, spray nozzles for stand and hot blasting. It is also used in rollers and other supports for the paper industry, extrusion dies, automobile pump, seals and seals between parts which turn or slide with respect to one another. Although the WC cobalt sintered carbides are the most important cutting tool materials, but alumina is also used as cutting tool material because alumina cutting tools can give high cutting speeds and are well adapted to the machining of hard metals. Moreover, it also be used for the metal coated with oxidized layers. They are much less expensive than the cemented carbide tools. Alumina is also good shielding material for applications in bulletproof jackets, protective coatings of helicopters or tanks where the need is to stop high-speed projectiles with speed of 10 into kilometers per second. For such applications, the material should be hard with high modulus and high strength under compression. Although boron carbide is a better shielding material and Kelver polymer is a suitable for lightweight shielding applications, and the alumina is also good candidate for shielding materials. Alumina is also used as a bioinert material in applications such as hip joint, prosthesis, knee joint, dental filter, and so on. Zirconia ceramics. The zirconia ceramics are of interest due to high toughness that can be achieved in them and also due to their very low thermal conductivity, which makes them very useful in thermal barrier coatings and applications such as coating inside the chamber of a jet engine, and due to its high refractive index, zirconia is also used as a cheap substitute of diamond in jewelries. The zirconia occurs naturally in the mineral badellite mainly in South Africa, and however the main source of zirconia is zircon and ZrSi4 in the beach sands in India. However, it is also found in Australia and United States. Now let us discuss about the structure of zirconia. Pure zirconia, that is ZrO2, has a cubic fluoride structure at temperatures above 2370, that is 2370 degrees Celsius, and on cooling it changes to a tetrahedral phase at 2370 degrees Celsius and then to a monoclinic phase at about 1100 degrees Celsius. The tetragonal to monoclinic phase transformations is accompanied by a volume increase of 4 to 6% and a shear strain of about 1 to 2%. Due to these changes, a pure zirconium body disintegrates on cooling with sintering, and pure zirconia can not be used as a sintered part of the pure form. The phase of zirconia also depends on the particle size. So, below a critical size, the high temperature phase can continue to exist at room temperature, but this crucial size is very small, that is 30 nanometers. The critical size can be increased to large values by adding some soluble oxides to zirconia, and these oxides are called stabilizers. So the most important of these stabilizers are calcium oxide, that is CaO, magnesium oxide, that is MgO, and yttrium oxide, that is Y2O3. So depending on the stabilizer and its content, the zirconia can be made to exist at room temperature in the tetragonal or cubic phase or a mixture of phases. So let us discuss the cubic phase structure of the zirconia ceramic. So as we have discussed that zirconium oxide has a cubic fluoride structure above 2370 degrees Celsius. So students, you can see on the right hand side the structure of zirconia. So in this structure, the oxygen ions are arranged in a simple cubic lattice. The center of the alternate cubic or the center of the alternate cube is occupied by zirconium ion. The structure can also be viewed as one in which the zirconium ions are arranged in an FCC lattice and the oxygen ions are placed at the corners of a smaller cube located within the FCC cell of zirconium ions. Now students, let us discuss the tetragonal phase structure of the zirconia ceramic. The tetragonal structure is obtained with a slight distortion of the cubic fluoride structure by a slight movement of the oxygen, which you all can see in this figure. Each set has two molecules with two sets of zirconium oxide distances of 0.2455 nanometers and 0.2065 nanometers. Now let us discuss the monoclinic phase structure of zirconia ceramic. So students, you can see the monoclinic structure in this figure. So the zirconium ions in the monoclinic structure have coordination number 7 instead of 8 in the tetragonal and the cubic forms. So there are two sets of oxygen ions which are on different planes, that is O1 and O2. The O1 atoms are tetrahedrally coordinated while the O2 atoms are triangularly coordinated. The zirconium oxygen 1 distance is 0.204 nanometers and the zirconium O2 distance is 0.226 nanometers. So students, in this figure you can see the three structures of zirconium oxide. The figure brings out the distortion needed to change from one structure to another. So all the three, that is cubic, tetragonal and monoclinic structures of zirconia ceramic are shown here. Stabilization of the high temperature phases. As mentioned earlier, the high temperature tetragonal phase is retained down to room temperature and lower if the particles of zirconia are below a critical size, which is 30 nanometers. So the stress induced tetragonal to monoclinic transformation can be used to enhance the toughness of the ceramic. As such fine particles are difficult to prepare, so it is necessary to have a critical size of tetragonal phase stability to be increased so as to make use of the transformation toughening. As also mentioned earlier, the critical size can be increased to large values by adding some soluble oxides called stabilizers to zirconia, and the most common of these, which we have already discussed are calcium oxide, magnesium oxide and yttrium oxide. So the one group of stabilizers have a low solid solubility in zirconia. The example of these are CaO and MgO. The phase diagram in this case is shown on the left hand side, which shows that at high temperature in the cubic phase field, a large amount of solute are stable. On slow cooling, the stabilizers separates out, leaving behind monoclinic zirconia. However, if the cooling is rapid, a cubic phase in which the needle-like particles of the tetragonal phase are present is retained at room temperature. This material is then aged in cubic and tetragonal phase field region to coarsen the tetragonal particles. This is necessary because small tetragonal particles do not undergo stress-induced transformation very easily. The cubic grains also increase in size during this treatment, and as a result, the material consisting of larger grains or larger cubic grains, that is 10 to 300 micrometers, with fine tetragonal grains inside the cubic grains is obtained. The material is called partially stabilized zirconia, and due to large grain size, these materials have a low strength of the order of 700 to 800 megapascal, and the strength can be increased if the fine powder prepared by chemical routes are used. The stabilizers, that is yttrium oxide and cerium oxide, have high solubility in zirconia, and in this case the cubic phase is stable down to room temperature together with some monoclinic phases. So if the material is solution treated, or if the sintering is carried out in the tetragonal phase field region or near the tetragonal cubic phase boundary region, followed by controlled coupling, then a metastable structure consisting of grains of tetragonal zirconia with grain size less than equal to 1 micrometer is obtained at room temperature. The tetragonal phase is retained due to the constraint imposed by grains on one another and extremely low mobility of the cations. The critical grain size for the spontaneous tetragonal to monoclinic transformation during cooling is between 0.2 to 2 micrometer depending on the solute content and solute types. These materials have a high strength and high toughness due to transformation toughening. So for the microstructures of the various types of zirconia, the reader should know that this type is known as tetragonal zirconia polycrystal. The particles of zirconia containing these solutes, that is yttrium oxide, that is Y2O3, and cerium oxide, that is CeO2, can also be stabilized in a tetragonal structure at room temperature. So the factors responsible for the stability of the tetragonal phase in pure zirconium oxide below a critical size are: first is the lower surface energy of the tetragonal phase. So the multi-domain structure of small tetragonal particles and the presence of coherency strains in the particle. Next is the zirconium oxide particles. So the zirconium oxide particles in a matrix such as alumina leads to the toughening due to the stress induced from tetragonal to monoclinic transformation in the stress field of a propagating crack. This results in the large enhancement in the fracture toughness. For example, strength and toughness of alumina can be increased from 300 megapascal to 3 to 4 meganewton per m to power 3 by 2 to 900 megapascal to 10 meganewton m to power minus 3 by 2 respectively in the zirconia toughened alumina. So students, let us summarize what we have learned in this module so far. So in this module, two of the important structural ceramics, that is alumina and zirconia, are described. So the first is alumina. So in alumina, we understood that the alpha alumina has a rhombohedral structure with the space group, which is already detailed in this module. The lattice parameter at room temperature when referred to hexagonal axes are A is 0.4759 nanometers and C is 1.299 nanometers with a coordination number as 6. The structure is best described as an AB-AB hexagonal closed packing stacking of the O2 minus ions with Al3 plus ions located at 2/3 of the octahedra interstitial sites. So the mixed covalent and ionic bonding we have also read in this module, and these two bonding result in very high hardness, that is 9 more on the scale, and a very high melting point can be achieved, which is 2050 degrees Celsius. The strong atomic bonding and hexagonal structure make the dislocation motion very difficult in alumina, and some basal slips on the basal slip system occurs above 900 degrees Celsius. So most of the alumina ceramics have siliceous phases at the grain boundaries, which flows and causes the deformation above the temperatures varying from 800 degrees Celsius to more than 1100 degrees Celsius depending on the purity of the alumina. So the properties of alumina which we have read are high elastic moduli, high hardness, good tribological properties and wear resistance. It also has good mechanical strength with high temperature stability. But not all at the same time. The properties have to be optimized for a given application by controlling the purity and the microstructure. So the preparation also matters, how we are preparing the ceramics. So it is prepared from bauxite ore. A thermochemical process is utilized where the heat treatment of the transition aluminas obtained from bauxite at temperatures of about 1100 to 1250 degrees Celsius, and then milling was performed where alpha alumina powder needed for the preparation of structural ceramics. So the applications depend upon the structural materials. The tribological applications of alumina are most important, and these include thread guides in textile industry, spray nozzles for sand and hot blasting, rollers and other supports for the paper industry. Some of the other applications are extrusion dies, automobile pump seals and seals between parts which turn or slide with respect to one another. Alumina also has application in cutting tool, as shielding material in bulletproof jackets, as protective coating for helicopters and tanks, as well as bioinert material, Zirconia. So the main raw material for zirconia is zircon, that is ZrSiO4, which is found in beach sands. So the details of the zirconia we have also discussed in this module, and the pure zirconia, that is ZrO2, has a cubic fluoride structure, which we have learned, and it is at the temperatures above 2370 degrees Celsius. And on cooling, it changes to tetragonal phase at 2370 degrees Celsius and then to monoclinic phase at about 1100 degrees Celsius, which can be easily understood from the phase diagrams. So the tetragonal to monoclinic transformations result in the increase in volume of about 4 to 6% and a shear strain of about 1 to 2%, leading to a pure zirconia body disintegration on cooling after sintering. So pure zirconia can therefore not be used as a sintered part in the pure form. Zirconium oxide, that is ZrO2, has a cubic fluoride structure, and the tetragonal and monoclinic structures are obtained by distortion of the cubic structure. The tetragonal phase of pure zirconia can remain stable at room temperature if the particle size is very small. So in the module, we read that various factors are responsible for the stabilization of the tetragonal phase below the critical size, which involves lower surface energy of the tetragonal phase, multi-domain structure, and the presence of coherency strains in the particles. So this critical particle size is increased to more practical micron levels by alloying with calcium oxide, magnesium oxide, and so on. Moreover, we have learned that the stabilization with yttrium oxide or cerium oxide can be utilized to produce a material called tetragonal zirconia polycrystal, which consists of grain of tetragonal phase, and in this the grain size is very less than 1 millimeter, and the material has high strength and high toughness due to the transformation toughening. So similarly, as in the case of alumina, we have read in zirconia also how the structure is changing from one to another with changing various parameters, like in case of tetragonal zirconium oxide particle in a matrix, the toughening is due to the stress induced when the tetragonal is transformed to monoclinic in the stress field and result in large enhancement of fracture toughness.